All right, everybody. Fantastic to see you all for this afternoon's Light in Quantum. We're very, very pleased to have you, Adam, join us here for the seminar. Adam joined us in NQCP back in January, or rather in Quantum Foundry as part of the big program. And you've been super, super busy looking at new labs and opportunities and so on. So we're very grateful for you taking the time to come here and tell us about the devil, which is not in the details, but in the details of the material.
That's right.
Thanks a lot.
All right. Thanks very much. Okay. So thanks everybody for coming. I appreciate you being here. My name is Adam Schwartzberg. So this talk is a little bit of a mix of things. I'm going to give a little bit of my background just so you have a flavor of where I came from and all of the weird things that I've done. I'll talk a bit about my transition into quantum and quantum computing and materials. So as we go through this, hopefully you'll get a better feeling for sort of what I've done. So first, let me go through my origin story. Like I said, it's pretty varied. So I did my bachelor's and PhD at UC Santa Cruz, which is just south of San Francisco. It's a very beautiful campus. It's a very hard place to leave. And many people end up stuck there for life doing weird jobs because they just don't want to leave. While I was there, most of my PhD work was on actually nanoparticle synthesis and characterization. So I worked on mostly gold nanoparticles. I did synthesis of these things called hollow gold nanoparticles, which is literally a core shell where the core is just liquid and the shell is gold. And you can tune the colors, which is useful for making pretty pictures, but it's also useful for things like surface enhanced Raman, where you want to tune the plasmon resonance to be on resonance with the laser that you're using for surface enhanced Raman. They also have very interesting ultrafast properties. So I did a lot of work on ultrafast transient absorption, where you can actually map out the radial breathing modes of these things, because they're literally bubbles of gold. And when you hit them hard enough with the laser, they oscillate. And that actually changes the resonant frequency of them. And so you can map out these coherent oscillations that exist in them. So in addition to nanoparticle synthesis and surface enhanced Raman and transient absorption, I also did biological sensing, because these things are good for biological sensing, and all kinds of crazy stuff. I did too many things. So from there, I moved not too far north to Berkeley. I did my first postdoc at UC Berkeley. There, my main program was on something called broadband coherent anti-Stokes Raman spectroscopy. So unlike normal Raman spectroscopy, this is a coherent process that uses femtosecond pulses. And a lot of what we did was actually looking at resist molecules. So one case was this, it's called hydrogen cell sesquioxane. I'm a physical chemist, so I can say that. I apologize to the physicists. Essentially, it's a cage of silicon and oxygen. It's more or less silica, but it's in liquid form. And so you can spin coat this onto surfaces, and it's used as a resist material for especially high resolution patterning. But it also is a particularly interesting material, one, spectroscopically, but two, you can learn things spectroscopically about how the material crosslinks, which informs how you can modify it to make it into a better resist. So from that, where I basically spent my entire time in a dark laser lab just shooting very short pulses and mostly blowing things up, I moved just up the hill to Lawrence Berkeley National Labs for my second postdoc, where I completely changed directions and went to fabrication and use of near-field probes. So again, going back to plasmonic materials, but this time doing actual fabrication. So I've shown an example here, but this is just one out of many where we actually take a near-field tip, or in this case, just a silicon nitride AFM cantilever, coat it with gold, and then use a fib to put a plasmonic feature into that. And then you can shine light through the back and actually take Raman spectra through the silicon nitride tip. And so here's just one example of a single carbon nanotube where we get something on the order of 20-ish nanometer resolution, optical resolution with Raman. And so that was mostly, honestly, it was about building the microscope that allowed us to do this. The fabrication was also hard, But at this time, this was in 2008 to 2010, AFM was more complicated, optics was more complicated, everything was just a bit harder. Things weren't as well integrated. Now, including optics with AFM is more done. This was like pretty early days for that. Okay, so that was 4 years of postdoc, and then I briefly went to Sandia National Labs, which I'm not going to talk about because I was only there for a year, and then I immediately came back to LBL, where I worked at the Molecular Foundry. So the Molecular Foundry, for those of you who don't know, is a user facility that is, oh, thank you, mood lighting. A user facility that's funded by the US Department of Energy, where we essentially, the original intent was to study and provide resources for nanoscale material science. So you can see all these different types of capabilities that exist. Each floor has its own speciality. I worked on the nanofabrication facility where I ran a program in atomic layer deposition, but also other materials and materials characterization and just general fabrication. Eventually, I became the facility director of that facility. And I just wanted to give you a really, really, really tiny snapshot of some of the breadth of the types of experiments that one might do at the nanofabrication facility in the Molecular Foundry. So I know probably quite a few people here are familiar with 2D materials. We also did work on 2D materials. So we actually developed a fairly unique process by which to grow tungsten disulfide and other disulfide materials, where we would grow atomic layer deposited transition metal oxide films and then use them as precursors in a tube reactor to grow the crystals. So these are single crystals that we grew onto a substrate, and then we handed these off to my colleague Alex Weber-Bargioni, who did STM measurements and actually was looking at individual defects in those TMD materials. We also had a big program on nanofluidics, where we fabricate nanoscopic, in this case 30 nanometer channels into I think this is PDM, I can't remember what this material is, but it's a resist material, and it's done by nanoimprint lithography. So you actually fabricate a very high resolution negative and press it into a resist, and you end up with a 30 nanometer channel. The especially tricky thing about these is not just a channel, but we also included plasmonic antennas into that channel. So if in the upper right hand corner you see this little bow tie thing, those are gold bow ties with a 30 nanometer gap to allow optical access, high field optical access into that channel. And then lastly, this is a more recent one, more 2D materials, where we put TMDs on top of nanofabricated plasmonic grooves essentially, and are actually able to measure plexitons in near field. So plexiton is a coupling of a plasmon and an exciton. It's an exotic particle. People like exotic particles these days. And you can actually measure these and modify them by pressing the AFM tip into that groove, causing strain and causing it to force into the groove. So all kinds of cool stuff. And so really, the thing that I really enjoyed about being at the Molecular Foundry is that there's this huge influx of ideas and people who want to do different things, and our job as staff scientists there was to help them. Whatever it is, as long as it can get through a review panel, our job is just to make their science possible. And for someone who really likes doing different things, there's a lot of cool opportunities. Okay, enough about that. Here comes the quantum. So in 2018, 2017, I was introduced to this guy, Irfan Siddiqui, who's at UC Berkeley. He has a very big lab on quantum computing, and he was interested in working with us because he had this problem of coherence times in superconducting qubits not really improving. And they would spend more and more time fabricating harder and harder to get better results, but it kind of petered out. And he really wanted to know what is limiting this coherence time. And his suggestion was that this might be due to stuff at interfaces. So all these little fuzzy things are different oxides that can grow on all the interfaces. And it's not just the surface interfaces, but it's also the interstitial interfaces between each layer that's deposited. And it can be oxides, but it can also be organics. It's all the stuff that basically is a result of fabrication. because as nice as our PowerPoint images are, the reality, of course, is completely non-ideal. And so the idea was, can we actually pick apart what some of the limiting factors for superconducting qubit coherence are, and do they have a relation to the materials? So the first thing we did, because oddly enough it was actually at the time quite difficult to find this, is we just made a fib cross-section of a Josephson junction and looked at it. And as you might expect, it doesn't look very nice. And I'm sorry, it's a little hard to see on the screen. But this right here, wait, I'm sorry. Yeah, this right here is actually the interface between the two layers. Yes, between the two layers of aluminum. So aluminum, oh, thank you, perfect. Aluminum oxide, aluminum, the junction is here, and you can see it's very rough. The grain structure of the aluminum is poor. Also, there's non-idealities. And when you look closer with TEM, it gets even weirder. And this is actually a nicer junction. But you can see that, one, there's aluminum oxide coating everything. In this particular case, there is this is actually on silica. So you don't see it here, but you also get silica at the interface between the aluminum and the silicon. And then the barrier layer of the aluminum oxide is not a nice, straight, perfectly even slice of cheese. It is something that's very rough, and it's determined largely by the grain structure of the aluminum that it grows on. And so that's not great. And if you look at EDS, where you can actually see the elemental map, you see essentially what's going on. All the blue stuff here is oxygen. And you want oxygen here. This is your Josephson junction barrier. You don't want oxygen here, and you don't want oxygen here, and you definitely don't want oxygen there. And so it's very clear that just looking at the Josephson junctions that something is not as one would imagine. However, the Josephson junctions are not really the biggest source of loss in the devices that we were looking at. The biggest source of loss in the coherence was actually from the resonators. So these are RF circuitry. And there's a lot of ways to lose energy in these circuits. And it was pretty well understood at this point that most likely the lack of improvement was coming from these resonators. So for those of you who are not familiar, this is basically what the qubit circuits that we were working with looked like. You have these capacitive pads. The Josephson junctions are at the middle of the H here. And then you have RF circuitry, essentially, to carry signals in and out. And so what we wanted to do was to look at how these interfaces are affected by fabrication processes. So if you kind of look in cross-section of these waveguides, what you have is everything we're doing here is niobium resonators on silicon. So you have your silicon substrate. You have these very long wires, essentially, of niobium. And you have two interfaces, essentially. You have the interface between the silicon and the niobium and the air or vacuum or whatever. And so we took cross-sections of these, and what you see is, of course, non-ideal interfaces. So at the silicon interface, not under the niobium, you have silicon and silicon oxide, and you have a mix of silicon states. It's not just pure crystalline silicon oxide. It's amorphous, and it's kind of just a mess. You can also look at the interface between the niobium and the silicon, and there you have a better interface, but there's still some oxygen. But you do, in most places, have epitaxial growth if you do it right off of the silicon. However, at the niobium, this is where the problem really starts. On the surface of the niobium, because the thing to keep in mind about the fabrication for all these is that you start with essentially a material, your niobium, that you've put down, and depending on how you do it, you always end up with some kind of resist that's covering everything. And you need to remove the resist and all the residue and all the process gunk that appears. And so the standard way that you deal with this is you put it into an oxygen plasma, which works very well for moving carbon, but it also works really well at oxidizing niobium and silicon and everything else. And the general practice at the time was that you just sort of left it there and assumed that it didn't really do anything, because in theory, it maybe shouldn't. Niobium oxide isn't a super lossy oxide by itself, so everyone assumed, fine, good enough. But what we did is we actually, in cross-section, made this EELS composition map. So for those of you who don't know, EELS is essentially a TEM technique that allows you to look at elemental, make an elemental map. And the different colors here are different ratios of niobium to oxygen. And as you go from the bottom, which is pure niobium, and the top, which is pure Nb2O5, you can see there's this gradient of concentration where you go from pure one to pure the other. And this is, again, very much outside of what you would expect from sort of this PowerPoint slab diagram of niobium oxide sitting on top of niobium. And then we have another collaborator at the Molecular Foundry, Sinead Griffin, who's a theoretician. And she went through and took all of the oxides that we found in this lab and did calculations on essentially the structures and what the magnetic impact of these materials are. And it turns out that the Nb2O5 is a non-magnetic material. However, anything off stoichiometry from pure Nb2O5 has some magnetic properties, which is really not what you want for superconducting qubits. You want to avoid any magnetic materials. And so with this, we thought, okay, maybe we have something here. There's something to the fact that maybe this niobium oxide is not good for what we're trying to do. And so we went about trying to get rid of it. And so the way that chemists get rid of oxides, the first thing you try is HF, which is what we did. It turns out HF is pretty good at dissolving niobium oxide. And so here you can see 3 different time steps where we've dunked these chips into buffered oxide etch, which is essentially HF, and with XPS measurements at these different time points. And so you can see that essentially what we have here on the top is essentially pure silicon with a tiny bit of silicon 2+. And at 0 time, we have silicon 4+, which is basically silica, amorphous silica. Same with the niobium. At 0 time, we're dominated by Nb2O5. And after 1200 seconds, you at least reduce that and have more niobium character. It turns out that it's with pure buffered oxide etch, it's almost impossible to remove all of the oxide, most likely because by the time you've gotten it out and cleaned it off and rinsed it and loaded it into the XPS, it's reoxidized to some extent. It doesn't have a protective layer the way that silicon does. Silicon has these protons that basically line the surface when you do HF dips. It appears that niobium doesn't really ever get that. So what we did is we took these samples, ran different dip times on resonators that had been fabricated. So these are all RF resonators, and we're looking at the resonator loss on this side. So longer bar means more loss, and this side, the thickness of the oxide. So longer bar means more oxide. And there's a correlation. So as you go to longer and longer etch times, you get less and less niobium oxide and better and better resonator loss, less resonator loss essentially over time. So this is essentially a confirmation that, again, the materials matter, the fabrication matters, the interfaces matter, everything matters. And even with this, we haven't gotten to the point where we've actually removed all of the problems because essentially, yeah.
Did you time more than 20 seconds?
Yes, we did. So the plot stops here because it plateaus and it just is flat. Because I think, again, at a certain point, even if you could remove, so you've basically removed everything, but by the time you get it loaded back into the cryostat, it's oxidized again. But the most interesting thing, perhaps, is that there is a difference between the oxide that forms under plasma versus the oxide that forms in air. So if you take these devices and you dip them in buffered oxide etch and look at them before the oxide etch and after, even if you leave it out for a week or month, a year, it doesn't matter. The quality factor basically stays the same once it's been dipped. Whereas it's much, much worse after it's come out of the oxygen plasma. And it's some combination of probably thicker oxide, but then I think it's also more diversity in the species of niobium oxide that you get from this plasma because you're bombarding the surface with radical oxygen ions. Okay, so at this point we knew that interfaces were important. And in the midst of this whole thing, we came to this conclusion. We didn't wait till this was in to make that conclusion. And we realized that we needed to basically build some capacity for understanding interfaces and perhaps fabricating devices that control the interfaces. And so what happened is we got funding for building a very large cluster tool that I will describe in a second. And I just want to say at this point that pretty much everything that I'm going to say from this point forward was done by other people who are smarter and better than me. So Maithili and Yash did, I would say, the lion's share. They were postdocs with me. They're still at the Foundry, actually, doing really nice work on the cluster tool. Ari, up here, staring at his coffee, is sort of the, I would say, facilities brains of keeping this cluster tool running. And Idar is over there. I stole him from Berkeley and brought him with me because he's amazing. And I just want to say one other thing, which is we have this thing at the National Labs, which doesn't exist other places, but it's called the Postdoc Lab Research Slam, where essentially postdocs get up and give a 2-minute pitch. And it starts at the lab level. So Yash went to LBL and did it amongst, I don't know, 50 or 60 postdocs, and he won that. And then they do it at a state level amongst another 100 people and won that. And last night he was in Washington, D.C. with all the winners from all the national labs, and he won his area for that. So yeah, it was very good. He's awesome, and I would have stolen him if he would have left California. Okay, so the cluster tool. Essentially what this is what I wanted to build was a system that would allow me to do different kinds of growth and different kinds of fabrication of materials, stacking materials one on top of the other without breaking vacuum so that we could build interfaces that were clean, but also include analytics so that we could actually look at interfaces, we could modify interfaces and have feedback between them. And so, with that in mind, also explore new materials, so not just conventional tantalum and niobium and aluminum, but grow new things, but also make sure that we can make devices that are at least as good as sort of the standard qubit device made out of aluminum and niobium. And so what we built was this tool here. It has a load lock that can basically load in 10 wafers at a time, so we can do some automation with this. We have an e-beam evaporator, which is essentially, they call it the quantum tool, but it's a Josephson junction making machine. It's an e-beam evaporator that has rotating and tilting sample holder so that we can do conventional JJ fab with aluminum. Then we have a sputtering chamber at the top. That's reactive sputtering. So the plan for this was to do nitrides, and I'll talk a little bit more about nitrides in a bit. And then 2 ALDs, so atomic layer deposition systems. For those of you who don't know, atomic layer deposition essentially allows you to grow materials sub-atomic layer at a time. So angstrom level precision over growth. It doesn't have the same degree of control as something like MBE because this is all done at low temperature, so you're not doing epitaxy or anything like that. It is most commonly used for passivation layers and for dielectrics. So in semiconductor industry, it is heavily used, but mostly for dielectric spacers. What do you mean by less than atomic layer? So it is less than atomic layer. So the reason is because ALD happens through metal organic precursors, gas phase metal organic precursors. So you can imagine a metal at the core and then big fuzzy organic things hanging off of them. And ALD is a completely self-limiting process, which means that you have these things bouncing around in a chamber, and when they hit essentially an OH group sitting on the surface, oxygen sitting on the surface, they will react, but they'll only pop off one of these organic things. And so when you expose the surface, you essentially will make I'll say self-assembled. It's not really assembled. It's randomly oriented attachments on the surface, and it's just these sort of like, you can imagine fuzzy golf balls covering a surface. But because of these fuzzy things, they don't go into close packing. The metal atoms are actually far apart from each other, relatively far apart from each other. And so the way this works is that once the sort of golf balls are covering the surface, any more of these metal organics cannot react with them anymore. And they just sort of bounce off. And so you purge out the metal organics and you come in with water or oxygen plasma or nitrogen plasma or whatever, and that reacts with the organics that are sticking up off the surface. Those leave and you're left with a metal oxide, metal nitride, whatever. But what's left behind is much smaller than those golf balls. And so each layer, you're talking like half an angstrom to an angstrom of growth for every cycle that you do of this. And that's less than a single atomic layer of the material. So in order to get one atomic layer, it depends on the precursor and it depends on the material, but you're talking a couple of cycles of this, a few cycles before you fully pack that surface and you go to the second layer. So now you know everything about ALD. Okay, so the ALDs were really there for one, because I'm interested in growing nitrides by ALD. So actually being able to grow the superconductor part of this by atomic layer deposition, but then having an oxide chamber so that we can do dielectric spacers, but then also passivation layers over the surfaces to protect from growing non-specific oxides on the surface. So we can decide, I want 1 nanometer of aluminum oxide, and I'm going to live with the loss of that, knowing that it's going to be less than the loss of whatever random niobium oxide that grows. The other thing that you can do with ALD, with an ALD system, is you can do atomic layer etch, which is actually the reverse of atomic layer deposition. So you can remove, in this case, it's about 1 atomic layer at a time, and actually create pristine interfaces, which I'll also talk about in a second. And then finally, there's an analytics chamber on here, which allows us to move the wafer after deposition in, and then carry out things like XPS or ellipsometry, other characterization techniques that can be done in vacuum. Okay, and this sort of became a part of a wider, I say molecular foundry initiative. This is actually fairly heavily pushed across the Department of Energy for automation, just general automation of things, trying to really take the human out of a lot of the experiments that we were doing. And this was partially coupled to the fact that while I was in the process of building this, COVID happened. We couldn't have humans in the lab anymore. And so all of a sudden, everyone really wanted to automate everything for obvious reasons. And so the idea of this was really to have this sort of closed loop feedback mechanism between robots that would do synthesis of some kind, characterization in situ or inline, machine learning, and then a feedback loop to optimize material growth. So while the tool wasn't explicitly built for that, it is actually capable of doing this because it can be more or less fully automated. The part that was the hardest actually, and is still actually not done, is the part where our AI machine learning code interfaces with the tool builder's code to run the tool. And so getting the AI to actually modify the recipes as it grows and give feedback is the most challenging thing, honestly.
So software attached to the instruments may not be compatible with some software.
Yeah. So to give you an idea, the company that made our cluster tool is Angstrom Engineering. They were excellent to work with, but they are a company that is used to building tools that sit in a clean room. Someone walks up to them and pushes a button. I want titanium nitride. And a wafer goes in, wafer comes out, it has titanium nitride. They are not used to having other people's software talk to their software. So they had no API. There were no handles to grab onto. And so we actually had to contract them to write the code to build a new version of their software that had an API that we could attach to. And like I said, it's still in progress. Okay, so really what What I wanted to do with this cluster tool and with this project was to not just look at individual components within, let's say, just look at the materials or just look at qubits, but I wanted to have a process loop where we could grow materials, do characterization. At the Molecular Foundry, we had a lot of characterization equipment, so we can look at the materials very, very carefully, but then also look at things like TC and superconductor properties, and then take those materials, knowing everything that we can about them, do device fabrication, and then do qubit or resonator or other kinds of relevant device characterization, and then take that feedback and put it back into the materials growth with the cluster tool and have a loop where we can actually control and examine the entire loop. Because the problem is, if you are missing any one of these things, it's very hard to understand how the fabrication affects the device. It's very hard to understand how the materials affect the fabrication or how the materials affect the device. And so you really need to have this whole thing working in order to understand the entire process. Okay, so as I mentioned, this cluster tool, it allows us to do resonator and qubit fabrication, obviously Josephson and junction fabrication. And a few of the materials that we have access to are nitrides, titanium nitride, aluminum nitride, niobium nitride, tantalum nitride, really any of the transition metal nitrides. We can do sputtering, again, of nitrides and metals, oxides by ALD, and then E-beam. Mostly we do aluminum, but we can do niobium and titanium as well. And the first thing that we set out to do with this tool was really to, like I said before, make sure that we could fabricate a device that would at least match sort of what other groups can do with aluminum superconducting qubits. Because the problem is we could go immediately and try and build a niobium nitride Josephson junction device, but if the device doesn't work, we don't know if it's because our fabrication is terrible. We don't know why. So we wanted to make sure at least we could make a conventional device that works well. So the first thing we did is we started with making sure that we had good substrate preparation. So I think a lot of these slides will be very familiar to many of you, but essentially we just did very careful surface preparation, did aluminum deposition, and then do high resolution microscopy so that we could see that we indeed did not have oxides at the interface. In the case of not using HF treatment, we could very clearly see that there was always a silicon oxide, which again you would expect, but it is nice that you can see it. And these measurements are all done on actual aluminum resonators, so after fabrication. So then next is to develop the optical lithography for making all the resonator circuits and all the low resolution parts. So we have just a standard chip that we did in collaboration with the Alpecipical group at UC Berkeley. We sort of just co-developed this thing. Honestly, he developed most of it, just as a standard chip to look at. And we have test structures, a 4-qubit design, and resonators designed for testing different materials parameters. Then we do E-beam lithography. So liftoff, deposition and liftoff of aluminum. So you can see we have, these are AFMs showing just essentially what you would expect, relatively flat. But if you look at the zoom in, you can see that if you're not careful, you end up with resist residue. So we went through great efforts to remove that resist residue, trying to be as gentle as possible so that we didn't completely bombard the surface with oxygen plasma. Then we do wafer dicing, and then test our just JJ test structures. So we made a whole wafer full of Josephson junctions, several wafers of Josephson junctions, and then test the resistance versus the dimension. And we're showing one figure here, but this was 6 months of work of trying to optimize the oxidation step in the Josephson junction fabrication. Because every tool is a little different, we really had to optimize our JJ Fab tool to make sure that our oxides were the right thickness, so that we get the right resistance, so that our final devices would have the right frequencies. Then we take those devices and we do the full step, wire bond, load them into packaging, load them into a fridge, cool them down, and measure them. And in this case, we're just looking at resonators. So this was the first step, was just to fabricate this kind of conventional resonators. And after, I would say, 6 or 7 quite bad results, we started actually figuring out how to do this and get decent results. And now we're to the point where we can get over 1 million quality factor on aluminum, which I would say is at least near state of the art for aluminum resonators. And this was the first thing that I really wanted to confirm, is that we could at least make resonator circuitry that kind of matched the state of the art. Then we look at the full devices, and again, we don't have a huge number of data points on these because, for a reason I'll mention in a second, but we were able to get T1 times on the order of 100 microseconds, which again is not record-breaking, but it is solid. And that's really all I wanted, is I wanted to have solid devices, and this was for 2 reasons. One, again, to confirm that we could do it. But then the other is because this is a user facility and we want to be able to provide samples to people that we know are not terrible. We had to be able to prove that we could make a standard qubit device that worked, that we could hand off to someone and they could go and measure it or do weird things to it, try different materials on top of it, whatever. Because we get a lot of requests for basic things, relatively basic things like this, because a lot of groups may have a fridge, but they don't have access to the fabrication. Or they may have fabrication, but they don't have access to an odd material they want to try. And so we have all the little pieces that we can help sort of plug these scientific holes. The reason that we don't have a ton of data on a lot of samples is because we're actually completely fridge limited, in that we don't actually have a dilution fridge in the Molecular Foundry currently. So we have to beg, borrow, and steal time on other people's fridges on campus, in the physics division at LBL, and that makes it very slow. So the turnaround becomes incredibly tedious, because not only do you have to wait for scheduled time, but if it's not your fridge and someone else from that group has to do something quickly, you're the first person to get bumped. And so you can make as many devices as you want, but you may only be able to measure 1 chip in a month or in 2 months. And this really handicaps the whole process. Fortunately, the Foundry will be getting a dilution fridge finally, I think this summer sometime. And so that will really help. But I think you all understand the need for this sort of high throughput technique, being able to actually get full feedback, because you can fabricate as many devices as you want and you can look at the materials, but until you've loaded them into a fridge and actually measured them, you don't actually know very much about them. Okay, so I'm going a little slow, so I may have to zoom through some of this, but let me hit the high points. So I think I've talked about this enough. Why we should care about better materials. So one is the interfaces. We've talked about that. And the same is true for all these materials. So tantalum is sort of the material of choice right now. It's largely because tantalum oxide is a more stable oxide. It seems to be less lossy, but it's still not ideal. And I'm just going to skip this. And so what we wanted to do, as I alluded to before, is use our sputter chamber to develop nitride-based materials. There's a variety of reasons. But essentially, the nitrides are harder materials. They have more stable oxides. They have less oxide. They also have very, very different properties from the metals. So their TCs are much higher. Their superconducting binding energy is higher. They also have higher critical fields, so they're good for different applications in many cases. But they can also be quite good for qubits. But the problem is that for Josephson junctions, everything right now is completely dependent on the aluminum oxide process. It's very well understood. Everyone uses it. But it's not something that you can transfer to a nitride easily. So the place we decided to start was actually on just looking at the nitrides themselves for things like the resonator circuitry. And so we went through quite a large process of exploring and developing these nitride materials. So doing materials growth. So this is all reactive sputtering, changing parameters, doing materials characterization, and then superconducting properties. Mostly this is TC, but you'll see we do some resonator measurements as well. I'm not going to get into the details of sputtering because I don't think I have time. But essentially, reactive sputtering is a complicated process. There are a lot of parameters that you can tweak, and those parameters, even though they sound relatively small, actually have a large effect on the material properties. So a lot of this process was actually developing capabilities on the tool to consistently produce identical results and also understand how the different properties affect the final material. So here are X-ray diffraction spectra of all of niobium nitride on 3 different substrates: magnesium oxide at the top, sapphire in the middle, and silicon at the bottom. And the main takeaway of this is that kind of what you expect to happen does happen, which is silicon has the largest lattice mismatch. So the lattice of the silicon is most different from the niobium nitride. Magnesium oxide is the closest. And as you go from silicon to magnesium oxide, it becomes more and more crystalline. However, on sapphire, even though the mismatch is quite high, you get much better quality materials than you do on silicon. Better quality being more epitaxial and more single crystal. We did X-ray reflectance and TEM cross sections, and you can get these beautiful epitaxial crystals grown off of sapphire with very little included oxygen. I think we have, yeah. So this is XPS data taken on these niobium nitride samples. The XPS spectra that you're seeing here are actually milled down a little bit into the material because these were not protected from the air, so they're slightly oxidized. But once you get down into the material, we do see oxygen, but we don't see any NB2O5 or NBOX. And we think this is because this is not a UHV XPS system, so there is oxygen in the system. So we always get a little bit of oxygen on the surfaces. But essentially, the ratio of niobium to nitrogen is essentially 1-to-1 once you get down into the film a little bit, a few nanometers down, which is good. It's what we expect. And in order to get this, we used a Rutherford backscattering to confirm the concentrations, because you really kind of have to do that to understand analytically what you have. So then we take these films, load them into our PPMS, which for those of you who don't know is essentially a very, very small stage cryostat that cools down very quickly, and run TC measurements on them. And you can see that the TC of the films is well correlated to essentially how high a quality the crystal is. So on magnesium oxide is the highest crystallinity, also has the highest TC. Silicon, lowest crystallinity, lowest TC, and the transition width correlates as well. We also did magnetic field measurements to get critical field. Yeah, so essentially map out the entire space. Then with those materials, we fabricate resonators. So these are identical to the aluminum resonators, but modified just to get frequencies in the range that we want, because the frequencies are different in niobium nitride than aluminum. And I just wanted to throw this up quickly to get everyone on the same page. So this is not our sample. This is sort of what you kind of expect to see for these resonator quality factor measurements. They always have this sort of sigmoidal shape. As you go to lower and lower power, essentially what happens is at higher power, you saturate defects, loss channels, and the quality factor increases. As you get down to the single photon level, you reach a point where the loss channels are no longer saturated and the quality factor decreases. And so this is kind of what you expect. And this shape actually correlates with the concentration and type of loss channels that you have in your chip, in your device. The reason I threw that up was because we don't see that. And it's not entirely clear to us why we don't see it. But I think maybe the most important thing to point out first is that the quality factors for this are not as good for aluminum, but they are significantly better than any other reported niobium nitride resonator that we could find in the literature. So we're very happy with that. But it is odd that you have this sort of linear power dependence. And either the TLSs are not saturated, or the TLS contribution is weak, or non-TLS losses are dominating the device. But again, this is something that's very difficult to do without doing a lot of measurements. And as I said before, we don't have a lot of fridge time. So this is something that needs to be explored further. And I just wanted to put up this comparison because I think it's kind of interesting. So we have niobium nitride on sapphire and niobium nitride on silicon. And on the right, it was grown at 600 degrees. And the interesting thing is that we know that the niobium nitride grown on sapphire has much better crystallinity, a higher TC, everything is better about it. However, if you look at the quality factors, they're more or less the same, which I find interesting because it's not necessarily what you would expect. And the here you can see the correlation of TC to deposition temperatures for niobium nitride and silicon. And one, you can see that they're pretty far apart. So the sapphire has much higher TC. They also move in opposite directions, which is why actually the quality factor for the high temperature silicon device is worse. It's actually because when you grow at high temperature, you start reacting your precursors, your niobium nitride reacts with the silicon and you form niobium silicide or something, which is a lossy material, and you don't want to do that. And I only put this up here to just reiterate that this correlation you wouldn't necessarily expect, and things like forming silicides are something that are not necessarily obvious to everyone. And it just shows, like, again, really there's a lot of details within the materials that are easy to overlook. And it's very important that you actually look at all of these things to understand where you're losing things. Okay, I'll go through this last part fast. So in amongst all of this, we had a collaboration with physics, our physics division at LBL, who make these dark matter detectors. For those of you who don't know, dark matter detectors are essentially phonon detectors. No one knows what dark matter is or if dark matter exists or really anything about dark matter. They don't know how to look at it. They don't know what it looks like. But the theory is that these things should be fairly massive. And if they interact with any kind of solid, they should launch a phonon, an athermal phonon. So
axiom hypothesis.
Yes, that's right. Yes, this is the operational principle of the group that we're working with. Yes. Sorry, I'm not a physicist. And so the devices are essentially slabs of material, silicon, alumina, gallium arsenide, with essentially a transition edge sensor on the top. So there's a collection fin that collects the phonons and a transition edge sensor that detects when a phonon interacts with it. It looks something like this, where you essentially have these wires with contacts, and when a phonon, so these are all run at cryogenic temperatures, they're superconducting. When a phonon interacts with them, it breaks a Cooper pair, it changes the resistivity of the wire. That causes a thermal overload, which then breaks a lot of Cooper pairs. So it warms up, increases the resistivity, then it cools back down, and it goes back to superconducting. And so these can be used for all kinds of things. It's not just this. These are also used for single photon detectors and all kinds of stuff. But the thing that's interesting to me is that unlike for quantum computing or many things, rather than trying to have a higher TC material, you actually want to have lower TC materials. You want to have materials that are very, very close to losing they're basically the Cooper pair is falling apart. So very low energy Cooper pair bonding. So the way that they go about this is they use something like tungsten or hafnium, which has a very low TC in the hundreds of millikelvin, because it's very close to falling apart. But there's a better way of doing this, which is rather than just having a superconductor that then loses its superconductivity, is you actually build essentially a really bad qubit. And you put that qubit on the collector, and when a phonon interacts with the qubit, it's even more sensitive and gives you even more feedback than just breaking of Cooper pairs. And I've kind of already said this. But essentially, there's this correlation where on the computing side, you would like to push perhaps slightly more to the higher TC, on the sensing side, the lower TC. And so what we decided to do was the tungsten is the material that's used for the transition edge sensors because it is the lowest TC that you can achieve for this particular phase. But hafnium is a close second. And we decided to try and make essentially a hafnium Josephson junction to make a full hafnium qubit. And again, it's a bad qubit. You don't want it to be a good qubit. What you want it to be is very, very sensitive and very lossy. The interesting thing is that even though this may sound fairly straightforward, this has not actually been done. So groups have been trying to make these things for years. There's a group at Stanford who's been trying to do this for a long time. And not to give away the end, but we beat them. They were working on it for many years, and we beat them in like 2 months. Stanford. So what we did is we essentially did the exact same thing that we do for aluminum Josephson junctions, but with hafnium. So we put hafnium into our e-beam evaporator, which is not the best way to make hafnium materials, but with some optimization of the growth of the hafnium and optimization of the oxidation of the hafnium, because we're doing this in the exact same way where we deposit one layer, oxidize, deposit the second layer, and we were able to make it work. I'm going to skip this because I don't think it's important. There is something kind of interesting about these, is that if you look at the function of the junction area to the resistance, it doesn't match aluminum oxide well. And this is most likely due to either resistivity in the hafnium or a slightly incorrect thickness of the hafnium oxide, or just the hafnium oxide itself. But you can't scale the hafnium junctions the same way that you would the aluminum junctions. You have to understand that interaction. We then cooled it down and did IV measurements, and sure enough, we see a transition. There's a lot of physics in this that, to be honest, I don't fully understand as well as my postdoc Yash does. But essentially, it is a JJ. It's a functioning JJ, and it is the first demonstrated hafnium JJ, and will soon be the most sensitive detector ever fabricated once we make a device out of it. OK, so I'm just going to give 3 quick slides about what I've been doing since I got here. I'll be quick, I promise. So we are in the process of building up a new cleanroom facility. So Idar and I have spent the last 3 months essentially talking to salespeople. So it's not a very sexy job, but someone's got to do it. And it's basically we're trying to fill out an entire cleanroom worth of stuff so that we can make all of our cool devices. My own projects, what I'm interested in doing, amongst many other things, but this is close to my heart because I have become an ALD guy, having not started there, is work on doing atomic layer deposition of nitrides. And this is for things like through silicon vias, but can also be used for passivation. Oxides and nitrides can be used for passivation of circuits so that you can essentially, as I said, remove all of the random crud that forms on the surfaces. But then also developing atomic layer etching processes so that we can do things like surface smoothing. So for photonic circuitry, this is very important. So you can take a rough waveguide and make it smooth, which is very nice. Interfacial cleaning. So you can actually do all of your disgusting fabrication and then clean all the surfaces of your messy material. And then the other thing it does is it allows you novel routes of fabrication. Because you're not tied to having your aluminum oxide happen in one chamber. If you can clean off that aluminum surface after it's been exposed to air, then you can add an aluminum oxide layer or whatever you want and fabricate a next layer on top of it. So it opens up a lot of different fabrication that's completely impossible now. But there's a lot of work to be done in just developing these etch processes. Atomic layer etch is something that's used very heavily in industry, but for very specific things that are not superconductors. And then finally, I just want to thank everyone that worked with me on this. This is some of them. The team at Berkeley was and is fantastic, and it was a great place to work, and I hope you enjoyed my talk.